Alright, so this is the section 3.1 lesson video for honors chemistry, and this is going to be part 1 of 2 videos. So let's get started and get through the first half. Alright, so chapter 3 is on measurement, and so what we're going to learn are some things like percent error. We're going to learn how to do significant figures, scientific notation. Eventually we're going to get into dimensional analysis. So some things you've probably already learned before, but some things might be brand new. A lot of people struggle in this section because of the math, so just make sure you pay attention. Alright, so many properties of matter have quantitative meaning, and that means that they have a numerical value. Okay, so if something is quantitative, it means it has a number associated with it. So if I said this cloth weighs 50 grams, that would be a quantitative meaning. Qualitative, on the other hand, would be a descriptive word. So if I said this cloth is blue, that would be qualitative. So a measurement is a quantity that has both a number and a unit. So 50 grams, 20 centimeters, things like that. The unit typically used in the sciences are those of the International System of Measurements, which is SI. And in scientific notation, a given number is written as the product of two numbers. You have a coefficient, like the 6.5, and 10 raised to a power, so times 10 to the 7. In scientific notation, the coefficient is always a number equal or greater than 1 and less than 10. So in other words, you should have one digit in front of the decimal place, or to the left of the decimal, when you're writing scientific notation. So scientific notation is something you've probably already seen before, but just in case, we'll go over it. So the first part says, write the following numbers in scientific notation. So first you need to figure out, well, where is the decimal originally? Well, if you don't see the decimal, it is automatically at the end. So here, I know it's at the end. Otherwise, sometimes you'll see where the decimal is in a number. So you want one non-zero digit in front of the decimal, so that means I want to move the decimal right here. So I want it to be 3.94. So then I just count how many times I move the decimal. Now notice you're counting the times you move the decimal, not necessarily only the zeros. So I moved it 1, 2, 3, 4, 5, 6, 7 times. So I can cut off all my zero placeholders, and so I'm left with 3.94 times 10 to a power. Well, the power comes from how many times you move the decimal. I moved the decimal 7 times. But then you have to decide, is it a positive 7 or a negative 7? So if the original number is really big, and by that I mean greater than 1, your exponent is a positive number. If your original number is less than 1, like for example these two numbers right here, and you move your decimal in the other direction, your exponent will be negative. So since my number was a large number, larger than 1, I'm going to put to the positive 7. All right, and if there was a unit, when you write something in scientific notation, let's say this had said meters, you put your unit at the end. A lot of people want to put it right here. That's not where it goes. All right, so let's look at our second one. So again, I can't see the decimal, so that means it's at the end. And I want one non-zero digit in front of the decimal. So I want to put it between the 2 and the 8. So I count how many places I moved it. 1, 2, 3. So I'm left with 2.8 times 10. Since my number, 2,800, is greater than 1, I raise it to the positive 3. All right, and that's all you're doing. What we're trying to do is make our numbers shorter so we don't have to list all these zeros, because in chemistry we're going to have really big and really small numbers to work with sometimes. All right, so here I can see the decimal originally is right here. I want one non-zero digit in front of the decimal, or to the left of the decimal. So I want to move it between the 5 and the 6. So I count over 1, 2, 3, 4. So I move my decimal 4 places. So what I'm left with is 5.67 times 10. So remember, I moved my decimal 4 places. But my original number is much smaller than 1. So instead of saying times 10 to the 4, I'm going to say times 10 to the negative 4. And if you notice, I have also moved the decimal in the opposite direction. So that's what makes it negative 4. All All right, so let's look at our last one. So our decimal's currently right here. We want one non-zero digit in front or to the left of the decimal. So I want to put it at the very end. So I count over 1, 2, 3, 4, 5, 6, 7. So I would put 2 times 10. And again, because my original number is less than 1, I put to the negative 7. Okay, so for numbers greater than 1, when you move your decimal to the left, you end up with a positive exponent. For numbers less than 1, when you move your decimal to the right, you end up with a negative exponent. All right, so sometimes though you may have scientific notation and you want to put it in standard notation. So to do that, we just start with the coefficient part of the number. So I have 3.22. Then it says times 10 to the 4. So I know I need to move my decimal 4 places, but I have to decide which direction. And remember, y'all, it's how many places you move the decimal, not necessarily how many zeros you're going to add. All right, so it's 10 to the positive 4. So that means my original number should be greater than 1, or a large number. So if I move the decimal this direction, my number is going to get smaller. However, if I move the decimal to the right, my number is going to get larger. So I'm going to move to the right, because 10 to the 4 means my number is a large number. So I go 1, 2, 3, 4. There's my new decimal. And then you just fill in zeros for the other places. Okay, so see, notice 10 to the 4 didn't mean I added 4 zeros. It meant I moved it 4 places, and in this case, I happen to add 2 zeros. Now, the only thing that I require is if you turn in this answer, I will mark it completely wrong, because you cannot have 2 decimal points. So make sure you go back and erase the one you don't want me to see, or you can just rewrite your answer. Now, as far as if you put the decimal point at the end or not, that's up to you. I don't require it for these. All right, so let's move on to the next one. So we have 2.1 times 10 to the negative 5. So I'm going to start with my 2.1. And so I know I need to move my decimal 5 places, but this is to the negative 5. So remember, when the exponent is negative, that means the number is very small. So if I move my decimal this way, my number is getting smaller. However, if I move it this way, my number is getting bigger. So I want to move it to the left this time, 5 places. So 1, 2, 3, 4, 5. There's my new decimal. I'm going to fill in some zeros. And so remember, erase the old decimal that you don't want me to see. Or, like I said, you can rewrite your number. Now, as far as whether or not you put the 0 to the left of the decimal, that is up to you. I'm not picky about that. I'm picky if you have 2 decimal points. Also, if I give you a unit, like say I had given this to you as kilograms, then you better make sure you have a unit on your answer also. Okay, but notice none of these have units, so we didn't have to worry about it. All right, so next one is 8 times 10 to the 2. So I'm going to start with 8. Remember, if you don't see a decimal point, it is automatically at the end of the number. So this one throws some people off because they can't figure out where to start it. So 10 to the 2 means it's a large number, greater than 1. So if I start moving my decimal in this direction, I'm going to make it smaller. So I want to move my decimal to the right 2 places. 1, 2. So there's my new decimal. I'm going to fill in my zeros and get rid of my original decimal. So my number is 800. All right, so last one. We have 7.90 times 10 to the negative 6. So since it's 10 to the negative 6, that means I need my number to be very small, much smaller than 1. So if I go in this direction to the left, my number does get smaller. However, if I move it this direction to the right, my number is going to get bigger. So I'm going to move it to the left 6 places. So 1, 2, 3, 4, 5, 6. There's my new decimal. And so then I fill in my zeros. So don't forget to get rid of your original decimal. Or like I said, you can just rewrite it. And as I've already told you, I'm not picky about whether or not you have that very left 0 before the decimal point. All right, so hopefully, like I said, this is a review and you already knew how to do scientific notation. All right, so next let's talk about the difference in accuracy and precision. So accuracy is a measure of how close a measurement comes to the actual or true value, whereas precision is a measure of how close a series of measurements are to one another. So when you are shooting arrows, you are clearly trying to hit the bullseye. So that's our actual value, is the bullseye. So if you look here, all 3 arrows hit the bullseye. So that means we were accurate, we got close to the true value or the actual value, and we were precise because all 3 of them were close to each other. On this one, if you look, I know it might be hard to tell since you are watching a recording, but these 2 arrows are actually on the white, and this 3rd arrow is in the bullseye. All right, so here we're not very accurate because we only hit the bullseye 1 out of 3 times, so that's not very accurate. However, you see how they're all still really close to each other, so it's still precise. Okay, now this is not a great scenario, but you know, at least they're close to each other, and we're kind of close to being accurate. One of them made the bullseye. Worst case scenario would be this one. None of them hit the bullseye, so it's not accurate, and they're not even close to each other, so it's not precise. Like, there's something to be said for if you get the wrong answer multiple times, because that means you probably are doing the same wrong thing. And if you get totally different wrong answers every time, that means that you're doing something differently wrong every single time. So it's just harder to pinpoint your mistake. So, you know, this scenario is better than this one, but of course in science we really want to be accurate. We want to get the right answer. But we want to be able to get the right answer over and over again. Okay, so think about like if you're doing a study on whether a diet pill works, and you get 100 people to take the diet pill. Well, let's say one person loses weight. Well, that's great. That was an accurate result. That's what you wanted. But let's say the other 99 don't lose weight. Okay, well then that wasn't super helpful. Okay, so we want to be accurate of getting the right answer, but we want to be able to keep getting the same answer over and over again. Those are the best scientific practices. All right, but let's talk about error, because in science, a lot of times you just don't get the right answer over and over again. So sometimes you're going to have error. So error is the experimental value minus the actual or accepted value. So the accepted value is the correct value. The experimental value is what is measured in the lab. So if it says like a student did this, or you did this in the lab, or the teacher measured this, those are your experimental values. The percent error is the absolute value of error, which of course is experimental minus actual, divided by your accepted or actual value times 100. Okay, and so in other words, this right here. All right, now what I want you to notice is I used actual up here and I used accepted down here. That's the same thing. It's just if I notice that they use different terms in different textbooks, I try to expose you to both terms, because I want to make sure that you always know what someone's talking about. Okay, so actual and accepted are the same thing. So error is just E minus A, experimental minus actual. Percent error is the absolute value of E minus A. That means whatever comes out of here must be positive, divided by A times 100. Since error is just E minus A, error can be positive or negative. Since percent error has the absolute values, percent error must always be positive. And the unit for percent error is going to be the percent sign. So let's look at an example. So it says a block of aluminum has a mass of 147.3 grams. So it's telling us this is the mass of the block. So this is my actual or my accepted value. A student measures the mass of the block as 138.9 grams. So since a student did this, this is my experimental. So then it says, what is the student's error? So error equals experimental minus actual or accepted. So I just plug my numbers in. So my experimental is 138.9 grams minus my actual or accepted, which is 147.3 grams. And so once I subtract that, I get negative 8.4, and my unit is grams. So the student was 8.4 grams off of what the actual was, and they were 8.4 grams short. That's why it was a negative number. And it's okay if error is negative. And then notice that it has the units of whatever the measurement was originally. Then it says, what is the percent error? So remember, percent error is the absolute value of E minus A over A times 100, where E is my experimental and A is my accepted or actual. So then I just plug my numbers in. So E is 138.9 grams minus my A, which is 147.3 grams, absolute values for that, divided by A, which is my 147.3 grams, times 100. All right, so when I subtract this, which we already did up here, I'm going to get negative 8.4. But because it's an absolute value, when I continue the problem, I'm going to change that to positive 8.4, or just disregard the negative in your calculator. So then I'm going to divide by 147.3 and multiply by 100. And when I do that, I get 5.70. And then the thing is, the grams is going to cancel because you have grams in the numerator and grams in the denominator. So the unit for percent error is the percent sign. Okay, so we're going to do percent error, percent yield, percent composition, lots of different percentages in this class. And so when it's percent something, the unit ends up being the percent sign. All right, so hopefully that wasn't too bad, just plugging into a formula. And so remember, accepted and actual is the same thing. They both can be plugged in for the A value. All right, so next thing is significant figures. So the significant figures in a measurement include all of the digits that are known plus a last digit that is estimated. So because it's plus a last digit, that means you are allowed to estimate one digit. So it's every number you measure and then one estimated value. The greater the number of significant figures, the greater the certainty implied for the measurement. Okay, so let's look at these two examples real quick. So here we have a piece of wood, and here we have a ruler that is labeled as 1 and 10. That's all we know. So I can't even actually measure any place values because the very first number I'm going to say, I'm already having to estimate. Okay, so I'm going to estimate this is about 5 centimeters. So since I've estimated the 5, I can't go on. What I mean by that is you can't look at this ruler the way it is and say, oh, it's 5.1348092 centimeters. That's what significant figures is about. You know how sometimes in your calculator you take two simple numbers like 27 divided by 13, but then you get all these decimal places? That means those numbers have not been actually measured. So you're reporting data that you're not actually sure about. Okay, so according to the way this ruler is set up, I can really only estimate it to be 5 centimeters. I can't go out any decimal places. Now, if I have a better ruler, then I can go out further. So see, on this ruler, I can actually measure, okay, for sure it's 5, it's not 6, but it's 5. And then I can now estimate a decimal place. Okay, so I can say, okay, well, it's a little past the halfway mark, so I'm just going to say it's about 5.7, or you might say 5.6. But again, I can't go any further than that unless I have a better ruler. So that's what significant figures is about. Again, I can't just say, oh, it's 5.70184. I have to stop once I've estimated one place. You can't keep going. All right, so let's look at how do you know when something is significant or not. So there are some rules for telling if a number is significant or not. And by a number, I mean a digit, because we're going to look at each digit separately. So every non-zero digit is always significant. So what I've done in my examples is I've underlined anything that is significant. So 254, those are all significant because they're not zeros. 65.43. They're all significant because they're not zeros. Zeros are the ones that are tricky. There are literally 3 rules just for zeros. So first, let's start with zeros in between the significant figures. I like to call them middle zeros. So see how the zeros are in between the non-zero numbers? And here the 0 is in between the non-zero numbers. Middle zeros are significant also. So because of rule 1, I know the 3 and the 5 are significant because they're not zeros. Since these zeros are in the middle, they are significant. So notice I underlined them also. Same thing over here. Since this 0 is in between the 1, 8, and 3, because those are significant, it becomes significant too. zeros before or to the left of the significant figures are not significant. Now, the important thing to remember is just because we say they're not significant, it doesn't mean they go away. Like, we still write them and we still use them, but I'll show you why it's important to know whether something's significant or not when we do calculations in just a few minutes. So the important thing is they're still there. Like, we'll still put them in the calculator and things like that, but it just helps us determine what our most accurate answer is. So, here's my significant digits. 7 and 9 and 2 are because of rule 1. They're not zeros. This 0 is significant because of rule 2. See how it's a middle 0? But these zeros are to the left. A lot of times I call them front zeros because they're at the front of the number. To the left are not significant. So notice I did not underline them. And here's another example. 0.6932. 6, 9, and 3 and 2 are because of rule 1. They're not zeros. But this 0 to the left, or the front 0, is not significant. So again, just because I didn't underline them, it doesn't change the number. Like, this doesn't turn into 7,902. It just means they're not significant. They were not measured. They're like placeholders. All right? So we talked about middle zeros. We talked about front zeros. So let's talk about back zeros. This is the trickiest one. Zeros after or to the right of the significant figures are significant if the number contains a decimal point. So if you can see the decimal point, it's significant. I'm not saying if you know where it is, because you can know the decimal point's right here, but we don't see it. If you can see the decimal point, then it's significant. If you can't see the decimal point, the back zeros are not significant. Okay, so let's look at this number. So according to rule 1, we know 2, 3, and 2 are significant because they're not zeros. According to rule 2, I know this 0 is significant because it's a middle 0. Now, according to rule 4, these back zeros are significant because I can see the decimal point. So I underlined all of them. All right, so let's look at this one. It's 63,000. So according to rule 1, we know 6 and 3 are significant because they're not zeros. But these back zeros, or zeros to the right, I did not underline them because I cannot see the decimal point. It doesn't matter that I know in my mind it's right there. If it's not written, those are not significant. So notice I did not underline those. However, and this is what throws people off, because it's like, what? How is this one significant but this one isn't? Just because they wrote the decimal. It makes a difference. So on this one, it's 570 point, like we have a decimal written here. So 5 and 7 are significant because of rule 1. They are not zeros. This back 0 is significant because I can see the decimal point. If the decimal point is written, then it becomes significant. All that means is here they were estimating 63,000. Here they didn't estimate, like they measured all the way through. Okay, that's all it's saying. All right, so last one. When something is in scientific notation, do not take it out. Just leave it the way it is. All right, just forget about the 10 and the power. Okay, so that's not even important. We're not going to underline any of that part. So we have 3.10 times 10 to the 3. So 3 and 1 are significant because they are not zeros. My back 0 is significant because I can see the decimal. The problem is if you start moving the decimal, it starts making it tricky and you start adding in extra significant figures that aren't supposed to be there. So don't move the decimal, just leave it in scientific notation. And then the last rule is easily forgotten, so just be careful. Numbers that can be counted and conversion factors have an infinite number of significant figures. So for example, if I pour a box of crayons out on your desk and said how many crayons are there, you're going to count them. You're not going to sit there and like measure how many crayons there are. So that has an infinite amount of significant figures because we're not questioning or estimating any of the places. Like you either have 14 crayons or you have 15 crayons. Okay, it's not like we're not talking about having half crayons and things like that. So you'll notice that by the unit. So like you measure meters, you measure seconds, you measure kilograms, you count puppies, you count cars, you count people. Other things that have an infinite amount of significant figures are conversion factors. So we'll talk more about those in section 3, but like 1 kilometer equals 1,000 meters. Both numbers, because this is a conversion factor, have an infinite number of significant figures. So again, that just means that these are not, there's no estimation going on here. 1 kilometer is literally exactly 1,000 meters. So there's an infinite amount of significant figures. Significant figures, I'll go ahead and tell you, is a really hard concept for some people to get, but it's all about just reporting your data accurately. So let's look at some. So it says how many significant figures are in each measurement. If you want, you're more than welcome to pause this and try it before I show you the answers. So in the first one, all of them are not zeros, so all 3 of them are significant. Remember, anything that's not a 0 is always significant. So that one's super easy. So on part B, we know the 4 and the 3 are significant because they're not zeros. And then we have middle zeros. So remember, front zeros are never significant. Middle zeros are always significant, and back zeros are only significant if I can see the decimal. So these are middle zeros, so they are significant. Remember, middle and front zeros don't have anything to do with where the decimal point is. All right, so part C. This one's in scientific notation. Remember, I'm going to disregard the 10 to the 23. I'm not going to move the decimal. So I know because of rule 1 that 6, 2, and 3 are all significant because they're not zeros. And then I know that this is a middle 0. See how it's in the middle? It's in between the other significant figures, so it is also significant. Part D, it says 22 meter sticks. So those are like a yardstick, but it's a meter, so slightly different. So would you measure those, or would you just count how many you had? You would count them. So because you would count these, this has an infinite amount. See how you can't underline to tell me an infinite amount. If you underline like this, I assume you're trying to tell me there's 2 significant figures and I mark it wrong. Okay, there are an infinite amount of significant figures. All right, so part E, hopefully you paused and at least tried a couple. Part E, we know 7 and 8 are significant. Oh, this is a perfect example because we have front, middle, and back zeros. 7 and 8 are significant because they're not zeros. Front zeros, zeros to the left of the significant figures, are not significant. It doesn't matter where the decimal is. Okay, both of these zeros are to the left of the significant figures, so neither of them are significant. A middle 0, so see this one is in the middle of the significant figures, is always significant. And then back 0, and see this is where some people get confused. They think when I say a back 0, I mean behind the decimal. I don't mean behind the decimal. Back 0 means behind the significant figures. So this 0, even though it's behind the decimal, is still in front of the significant figures. So it's what I would consider a front 0. So these are front zeros. This is a middle 0. This is a back 0. All right, so I can see the decimal. So this back 0 is significant. Remember, back zeros or zeros after the significant figures or to the right of the significant figures are only significant if I can see the decimal point. So for part F, 5 is significant because it's not a 0. These 3 zeros are back zeros. However, even though I know the decimal point is right here, I cannot see the decimal point, so these zeros are not significant. And again, just they're placeholders, so it doesn't change the number to 5. It's still 5,000. They're just placeholder zeros. All right, so part G, we know 1 and 7 are significant because they are not zeros. Here is a back 0, a 0 after the significant figures, but this time I can see the decimal point, so it is also significant. That means it was measured instead of just being a placeholder. All right, so the rules take some time to getting used to, but really if you can just remember, front zeros are never significant, middle zeros are always significant, and back zeros are only significant if you can see the decimal point, then it's not that tricky. So again, if you didn't pause the first one, go ahead and pause it and try these real fast, and then we will look at them together. Let me make sure I'm keeping up with where I need to end my video. Okay, perfect. It's after this slide. All right, so I'm going to assume you paused it, and let's go. So 5, 7, and 3 are significant because they're not zeros. These 2 zeros are to the left or in front of the significant figures, so neither of them are significant. This 0 is in back or to the right of the significant figures, so it is significant because I can see the decimal point. So hopefully you got that one right. Part B should be super easy. None of them are zeros, so they are all significant. All right, hopefully you got that one right. Part C, we know 1, 3, and 4 are significant because they're not zeros. All of these zeros are front zeros. Remember, a front 0 means it's before or to the left of the significant figures, not to the left of the decimal. To the left of the significant figures. So none of those are significant. They are all placeholders. All right, and then last one, part D, remember for scientific notation, don't move the decimal. Don't worry about your 10 power. 2 and 3 are both non-zero digits, so they are both significant. All right, now like I said, I know it's a little confusing about what does it mean when it's not significant, how does that alter the number? Well, if you watch the next lesson video, we will go over why we use significant figures, and it's mainly so that we can use them in calculations. But you gotta learn the rules first, so the rules are a little tricky until you actually use them.